Hi, I'm Lily, and I am pleased to present to you BaysRays, a method for uncertainty quantification in neural radiance fields. Neural radiance fields, or NeRFs, are 3D representations that take as input a set of posed images and learn a 3D field that can be rendered from novel views. NeRFs, regardless of their architecture, learn to map a 3D position to a color and density value. These values are then integrated through volume rendering to compute array color. The network parameters are optimized via a photometric loss comparing true and predicted colors of scene views. In this paper, we pose a crucial question. Can we rely on the predicted values by NeRF? Recent work by Warburg et al. Reveals a performance dip in NeRFs on test views when there is a distribution shift between train and test cameras. Observing NeRFs' predicted color and depth on test views, notable artifacts like floaters become apparent. This indicates unreliability in many predicted values by NeRF. Our hypothesis attributes these artifacts to the uncertainty stemming from information gaps in training views. Hence, we introduce BaysRays, a fast post-hoc method for quantifying uncertainty in any pre-trained NeRF of arbitrary architecture. The resulting uncertainty field can be applied for removing artifacts. To do so, we draw inspiration from classic uncertainty quantification in photogrammetry. In photogrammetry, uncertainty of the predicted 3D point position is the distribution of possible deformations on the predicted position such that it remains the same projection on the training views. Greater variance in this distribution signals increased uncertainty in the predicted point positions. NeRFs show a similar form of geometric uncertainty. For example, textureless areas like the laptop screen in this scene can produce geometric ambiguity when seen from limited camera angles during training. In such instances, the geometry can be deformed without affecting the photometric loss. Utilizing this concept of deformation, we redefine the NeRF formulation. Each query point undergoes a deformation before being mapped to its density and color. Our deformation field is parameterized by a trilinearly interpolated grid of deformations. The updated photometric loss becomes equivalent to the negative log posterior function of deformation field, with regularization ensuring small deformations. Since the NeRF model is already optimized, a zero deformation is a local minimum for this loss function. Now that we know the mode of the posterior, how can we find the covariance to get uncertainty? We employ the Laplace approximation as a well-suited tool. The Laplace approximation states that at the local minimum, the posterior can be approximated by a Gaussian distribution. The covariance matrix of this distribution is the negative inversion of the log posterior at local minimum. Under reasonable regularity assumptions, the Hessian simplifies to Jacobian transpose Jacobian. This yields our ultimate formulation of uncertainty at zero deformation. Here are some results. We can find uncertainty both on floaters within the scene and on the unseen areas. We can threshold the spatial uncertainty values in volume rendering to remove the floaters. Our uncertainty extraction does not rely on pre-trained models for denoising, and it only takes less than 2 minutes to run on a scene. Further, we do not need any access to training images or to perform explicit FROSTEM checks against the training cameras. Additionally, our method correctly identifies high uncertainty on textureless areas. We show that when we use the best uncertainty threshold per scene, our method achieves the best image quality while maintaining better coverage of the rendered images. We compare our model with previous uncertainty prediction methods based on Bayesian neural networks and brute force ensemble training. Our uncertainty exhibits superior correlation with depth error compared to Bayesian networks while having a similar performance to the more resource-intensive brute force methods. Here are some more results. Finally, we integrate our uncertainty quantification in NeRF Studio that allows interactive floater removal. Thank you for listening. More results at BaysRays paper.github.io.